Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to subscribe and share my videos to your friends and to your friends' friends. This is the only way you can help me promote my channel because I designed it to have so many lecture videos and sample problem videos so that you will no longer proceed to other vloggers. It is tiring on my part, and the only way you can keep me going and refreshed and inspired to do more lecture videos and sample problem videos is by helping me promote my channel. Ahoist is formed by connecting bars BD and BE to member ABC, neglecting the weights of the members, and assuming that all connections are ball and socket joints. Determine the magnitudes of the forces in bars BD and BE in terms of the applied load P. So here is the figure for the solution. Remember, these are ball and socket joints. BD and BE are two force bodies except for C or ABC. So FBD is assuming compression, so 3J plus 4K over square root 3 square plus 4 square. So FBD in vector form is magnitude of FBD. It is directed assuming compression, so rightward and upward. So FBD is equal to zero point 0.6I plus zero point 0.8K. Likewise, FBE is negative 4J plus 4K over square root of 4 square plus 4 square. So FBE is equal to magnitude of FBE, quantity negative 4J plus 4K over square root of 4 square plus 4 square. So it is magnitude of FBE over square root of 2 times quantity negative J plus K. And let's transmit it at E as shown. So leftward and upward. Then at C we have CX, CY, and CZ because it is a ball and socket joint. So summation moment about X 0. So we have FBE equals FBE over square root of 2 times 4 by right thumb rule. Then minus 0 0.8 FBD times 3. So from here we can relate FBE in terms of FBD. FBE is equal to 0.8485 of FBD. Then summation moment about CY0 or MCY0. By right thumb rule, we have P times 6 plus 4 is 10. Then minus 0 0.8 FBD times 4 minus FBE over square root of 2 times 4. Replacing FBE by 0.8485 of FBD. From there, we can now solve for FBD in terms of P. So P times 10 minus 3.2 FBD. 4 over square root of 2 is, so minus 2 square root of 2. FB is 0.8485 FBD. Solving for FBD, FBD is equal to 1.786 P. It is compression as expected, but you may not indicate because we are just told to determine the magnitudes of the forces in bars BD and BE. So substitute FBE 0.8485 of 1.786 P. So FBE is equal to 1.515 of P. So that's it for this problem. The 40-pound homogeneous door is rigidly attached to the bent bar ABC. The assembly is supported by a thrust bearing at A and a slider bearing at C. Determine the vertical force P required to keep the door in equilibrium in the position shown. Neglect the weight of bar ABC. So the direct way of solving this problem is to sum up moment about an inclined axis, but I think you might not like that solution. So let's put the reaction components and the weight of the homogeneous door. So we have AX, AY, and AZ at A. We only have CX and CZ at C because it is a slider bearing at C. So let's have the weight, 40 pounds. First, summation moment about AY so that we can have CZ and P as unknowns. Then summation moment about AX so that same unknowns are involved. So moment AY equals 0 by right thumb rule. We have CZ times 16 equals CZ times 16 plus 40 times half of 21, 10.5, and minus P times 21. So simplifying, 21P minus 16Z equals 420. Call that equation 1. Then moment about AX 0. By right thumb rule again, we have P times 26 plus 7.5 is 33.5. CZ times 33.5 plus 2.5 is 36. Then plus P times 33.5 minus 40 times half of 26, 13, plus 7.5, 20.5. So minus 40 times 20.5. Simplifying, 33.5B plus 36CZ equals 820. Solving these two equations simultaneously, we can now solve for P. P is equal to 21.86 pounds. So that's it for this problem. All connections of the structure are ball and socket joints, except for the slider bearings at A and O. The weights of the members may be neglected. Calculate the forces in members BE and CF. So here's the figure. So we have slider bearings at A and O, so only two reaction components, no reaction component along the axis of the shaft. Then at D, we have three reaction components. So we have the required forces in members B and CF. We have two force bodies for BE because these are smooth pins, as well as CF. So let's assume tension for each case. Then we consider the free body diagram of the upper part. Let's transmit the forces in BE and CF as shown in the figure. So FBE in vector form is magnitude of FBE, quantity 240I to the positive x-axis, then downward negative 320 along Z. So negative 320K over square root of 240 square plus 320 square. So FBE is magnitude of FBE times quantity 0.6I minus 0.8K. Then let's have the components at B. So again, at A, we have AX and AZ only. At D, we have DX, DY, and DZ as reaction components. Then let's transmit this components of FBE. So positive 0.6 FBE towards the positive x-axis, then downward 0.8 FBE. Then since CF is vertical and it is a two-force body, so it is just downward. So if we sum up moment about dy, we have BE and CF, the unknowns. 0.6 FB passes through dy, so it has no moment about dy. Then we can relate FC FBE in terms of FCF. So considering the FBD of the above shown, MDY equals 0 by right thumb rule. So we have 0.8 FBE times 240 plus FCF times 240. Cancel out 240, then FBE is equal to negative 1.25 of FCF. Then let's remove these reaction components. Let's have the free body diagram of the lower part and transmit the components of FBE and FCF as shown. So same at O, we have OX and OZ only. At G, we have GX, GY, and GZ. And let's transmit the components. So remember, it was tension, so zero point 0.6 FBE will now be rightward and upward, 0.8 FBE. Then CF will now be upward, FCF. So same equation, summation moment about GY equals 0 by right thumb rule. So we have equals 320 times 480 minus 0.8 FBE times 480, then minus FCF times 240. Replacing FBE by negative 1.25 FCF, we can now solve FCF. So 0 equals 320 times 480 minus zero point 0.8 of negative 1.25 FCF times 480 minus FCF times 240. Solving for FCF, FCF is negative 640 newtons, so it means FCF is compression. So FCF is 640 newtons compression. Then substitute FBE is negative 1.25 of negative 640. So FBE is equal to 800 newtons positive, so tension. Frame ABCD is supported by a ball and socket joint at A and by 3 cables. For A, 150 mm. Determine the tension in each cable and the reaction at A. So problems on 3D rigid body, 3D rigid body equilibrium are easier than 2D. So you just need to practice and solve a lot of problems on 3D rigid body equilibrium. So remember A is 150 mm. So let's have the components. So for FBE, we have it is towards the negative x-axis for 80 and towards the positive z-axis. So I will not show it anymore. So the x component is 480 tension BE times 480 divided by square root of 480 square plus 200 square. So that would be, so for A, which is a ball and socket joint, we have AX, AY, and AZ. Let's assume positive reaction components. Then at CF, because it is parallel to the XZ plane, then it is horizontal, so it is just tension CF. At B, 12 over 13 of tension BE, where 12 over 13 is 480 divided by towards the negative x-axis, 480 divided by square root of 480 square plus 200 square. So 12 over 13 tension BE. Likewise, the Z component, which is forward, is 200 divided by square root of 480 square plus 200 square, and that is 5 over 13 tension BE. For GD, it is just upward and backward. So for this x component, which is negative, so towards the negative x direction, it is 480, which is this, divided by square root of 480 square plus 140 square, and that is 24 over 25 tension dg. The vertical component is 140 over square root of 480 square plus 140 square, so it is 7 over 25 tension d. It has no z component. It lies on the xy plane. So that's the free body diagram. So summation moment about ax 0. If we sum up moment about ax 0, by right thumb rule, we can solve the tension in dg because DCF is not involved, it is parallel. This component of tension BE passes through AX axis, and this component of tension BE is parallel to AX axis, so we can solve tension DG. So we have equals 7 over 25 tension DG times 300, then minus 350 times A, where A is 150. 350 times A minus 350 times A, where A is 150. So tension DG is equal to 625 newtons. Moment about AY axis to solve for tension BE. So by right thumb rule, 24 over 25, this is positive sense. 24 over 25 times tension DG, which is 625, and the moment arm is 300. Then minus 12 over 13 of tension BE times 200. Times 200. So from there, we can solve tension BE. Tension BE is 975 newtons. And finally, summation moment about AZ 0. So these are not involved. We can solve tension CF. So summation moment AZ equals 0. Tension CF times 140 plus 24 over 25 of tension DG, which is 625 times 140, then minus 350 times 480. So we can now solve tension CF. Tension CF is 600 newtons. Then for the reaction components at A, summation forces X 0, Rx equals 0. So we have AX minus 12 over 13 of tension BE, which is 975, minus 600 tension CF, and minus 24 over 25 tension DG, which is 625. So AX is 2100 newtons. Then Ry equals 0, summation forces Y equals 0, equals AY plus 7 over 25 tension DG, which is 625, then minus 350. So AY is equal to 175 newtons. And finally, RZ equals 0. So we have AZ plus 5 over 13 of tension BE, which is 975. So that's only it. So AZ is equal to negative 375 newtons. So in vector form, the reaction at A is quantity 2100 I plus 175 J minus 375 K newtons. The bent rod ABDE is supported by ball and socket joints at A and E and by the cable DF. If a 60-pound load is applied at C as shown, determine the tension in the cable. So we have reaction components at A and E. The best way the direct way of solving this is to sum up moment about this inclined axis AE, then we can solve tension in DF directly with just one equation. But I will not do that because definitely you will not like it, and maybe you forget about the expression for moment about axis, an inclined axis. So let's just solve it by ordinary solution. So let's have the tension dF in vector form. Tension dF times quantity negative 16i plus 11j, then minus 8k over square root of 16 square plus 11 square plus 8 square. dF is towards the negative x-axis, 16, that's why negative 16i, upward along y, 11, then backward along z, negative 8. So in tension dF is magnitude of tension dF times quantity negative 16i plus 11j minus 8k over 21. So let's transmit it at d on d. So 16 over 21 dF, 11 over 21 dE, and 8 in that direction over 21 dF. You can also move it at f if you want, but I put it here so that we can easily solve for AY. That's the plan. Reaction components at A, reaction components at E. So if we sum up moment about this axis here, EX 0, then we can solve for AY. Only AZ is passing through EX, AX is parallel to, so we can solve for AY. Then the last part is we sum up moment about EZ0, then we can now solve this tension because only one component is required. So moment about EX equals 0, by right thumb rule we have AY equals AY times 24, then minus 60 times 14. So we can solve AY. AY is equal to 35 pounds. Then summation moment about EZ, 0. So we have 11 over 21 tension DE times 16. Then plus AY, which is 35 times 7. Then minus 60 times 16. So from there we can solve for the tension. So which is shorter in solution than the direct way of summation moment about inclined axis AE. So that's it for this problem. This is the last part. I hope that you were able to follow the solution by practicing, by solving more 3D rigid body equilibrium problems. You will be accustomed to solve such problems, and you will notice that it's only a matter of looking for the axis, appropriate axis, where you sum up moments to solve for the required. And the solution is shorter than the 2D rigid body equilibrium problems.